Hello everyone, I'm Siddhartha. Today I am going to present my study on radiation damage behavior of nickel Inconel multimetallic layered composite for implementing them as a nuclear fuel cladding application in molten salt reactor. Here we have used atomistic simulation process to study the radiation response of this particular nickel Inconel multimetallic layered composite. So for the safe operation of the molten salt reactors, it is very much important to choose appropriate nuclear material. Nickel-based alloys are becoming a prime candidate as the fuel cladding as a fuel cladding material because of their high recombination rate and superior structural strength. And the higher recombination rate actually helps to retain the structural stability and the mechanical properties of the material during the high corrosive and the radiation environment, because the defects that form during the radiation application, those defects are going to recombine themselves and retain the structural property, and that's why the recombination rate is very much important for the nuclear reactor. In this study, we have investigated the nickel Inconel multimetallic layered composite because because the multimetallic layered composite has a lower oxidation tendency and lower hydrogen production tendency. But in the conventional zirconium alloys, they have very higher oxidation tendency and they produce vast amount of hydrogen, which leads to a reactor meltdown accidents like Fukushima that happened a couple of years ago. The defects and the voids formed in the material can impair the mechanical strength and the dimensional stability. So it is very much important to study the material behavior under the reactor-like radiation environment for designing next generation nuclear reactor. In this study, we have investigated different composition of nickel and Cornell multimetallic layered composite, and we also investigated the 800H nickel structure. So here are the Inconel composition that we have used, and we have also used the ZVL modified EM potential to define the interatomic interaction at a very higher energy during the cascade simulation. Here we have introduced a primary knock-on atom energized with 10 keV energy to initiate the cascade at a very high temperature of 1000 Kelvin. We have used the successive cascade algorithm to reach up to a DPA level of 0.5. So to get into this radiation dose level, we have to introduce a 250 primary knock-on atom into a structure. So we have used the shrimp calculation to calculate the value of DPA for each primary knock atom in the nickel Inconel heterostructure, and we have set up the shrimp simulation with the same setup that we have used in the MD, and with the same structural conditions that we have in our molecular dynamic simulation. And after the calculation, we have got the DPA level of 0.002 DPA for each primary knock-on atom in our structure. So in this slide, we have presented the mixing profile of different at different DPA level for iron and the chromium atom due to the radiation cascade for 5 different Inconel nickel multimetallic layer composite that we have used in our simulation. If we look closely in those mixing profiles, then we can see that the tendency of the chromium, the mixing tendency of the chromium is quite higher than the iron atoms. Moreover, this mixing tendency has a very linear dependency with the radiation dose. In this figure, we have presented some structural response parameter under the radiations. In figure A, we can see the increased mean square displacement at a very at the thermal spike at the thermal spike time period of the cascade, and we can see a lower uh, mean square per displacement in the ballistic uh, time frame in a time frame of a cascade of a particular cascade. So in the figure B, we can see the accumulation of defect in the initial, which is very smaller, and at the final cascade, it gets very higher, which is quite normal, because the radiation actually increases the number of the point defects. In the figure C, the number of the defects has been plotted as a function of the radiation dose, and there have been a linear relation between them. We have plotted the thickness of the interface as a function of the radiation dose, and you can see as the radiation dose increases, the thickness of the interface also increases. So in the other figure, we have shown the defect formation throughout the simulation, and in the insert figure of that figure, we have showed the recombination process in a particular cascade simulation. You can see the defects get lower so when the recombination process starts, as the recombination process goes on actually. So here we can see some plots for the diffusion coefficient as a function of the radiation dose, and from those graphs you can see the radiation dose, the diffusion coefficient has very linear relation with the radiation dose, and the nickel 56 and chromium 23 iron 21 has a very high diffusion coefficient uh, compared to the other structure that we have used in our simulation. The diffusion and also the diffusion coefficient doesn't vary that much depending on the composition of the Inconel, but as the structure of nickel 56 and chromium 23 iron 21 has a quite higher percentage of nickel and a higher percentage of chromium, so that's why they have little bit higher diffusion coefficient, because the chromium has very lower migration rate, so they diffuse faster and they create some defects, and that at the presence of the defect, the migration barrier for the nickel also get lower. So that's why the nickel atom also starts to diffuse faster and create some defects, and that actually accelerate the diffusion. So that's why we have get the faster diffusion for the nickel 56 and chromium 23 and iron 21. So these are the result actually we can summarize from our findings of the study. So radiation induced mixing actually occurs due to the radiation, as the radiation dose increases, and the radiation dose increases with the number of Fermi knock-on atoms. During the radiation induced mixing, during the cascade simulation, radiation induced mixings are mostly done during the thermal spike stage of par cascade simulation. And in our simulation, from the parameters that we have got from, we can say that the 800H nickel multimetallic layered composite have a very high resistance, high radiation resistance, and they have the highest percentage of iron that actually uh, they have the highest percentage of iron that among all the structure that we have used. And we can see the chromium has very lower migration barrier, so that's why they have a very high tendency to accumulate the defects and thereby create the diffusion. And the presence of the defects also lowers the migration barrier for the nickel, and that also enables the nickel to diffuse faster and create some defects. And also the defect accumulation and the thickness of the interface has a very linear relation with the radiation dose. And also we can see from our very initial image that the sharp interface of the nickel-Inconel heterostructure gets actually gets thicker when we introduce primary non atom and increase the radiation dose. So in the future work, we will try to see how the grain boundaries actually affect the radiation damage in the material, and we will see the radiation-induced segregation of different elements using the variable constraint semi-grand canonical Monte Carlo simulation. So here are my collaborators and the funding agencies. So I want to thank them.